Hello, and welcome to 9.2 Graphing Simple Rational Function Notes. So, we're just continuing on our journey through our rational functions. And last time we talked about direct and joint variation, and today we're just going to talk about our rational functions. So, first of all, what is a rational function? That is just a function in the form of f of x equals p of x all over q of x. Now all this is saying is an expression with x on the top and an expression with x on the bottom. So consider the rational function y equals 1 over x. Now this is just a generic function. It's one of the most simple rational functions that we know. So for this first example, we're just going to do everything based off of this function. So looking at this, what are the possible values of x? So I want you to think about what values could we put in to our x here. Well, you can put any number you want to in here, so that would be all real numbers. By writing this, that means we can put a decimal or a negative number. That's just opposed to our whole number. All whole numbers are all natural numbers. So by saying all real numbers, that means you can put anything in your x. But we have one restriction. Our x cannot equal 0. If we have 0 in the denominator, this becomes undefined. So that is why we can't have x equaling 0. So the way I would write all real numbers is I would say all real numbers, but x cannot equal 0. So this is how I would write that. And then what are the possible values of y? So what possible values are we going to get for our y? And this is the same thing. It's going to be all real numbers. That's the way to write that. But our y is not going to be equal to 0. No matter what we plug in for our x, we are never going to get 0 for y. The only way we would get 0 for y is if we had a 0 in our numerator, or this thing was multiplied by 0, which neither of that is the case, so we will never have a y value of 0. Okay? And what we call these two restrictions here, x equals 0 and y equals 0, we call these asymptotes. Now, an asymptote is just a line that represents impossible numbers in a function. Okay, so in this case, we can't have x equaling 0 and we can't have y equaling 0. So, based off of this, the equations of our asymptotes are going to be x equals 0 and y equals 0, because these lines represent impossible numbers for this function. And just as a reminder, our x equaling 0, that's a vertical line. And way to remember it, if it's x equals 0, it crosses the x-axis, and then y equals 0, that's a horizontal line. And that will cross the y-axis when we draw that in. So, if we were to graph the function y equals 1 over x, we have to make sure that we draw in our asymptotes. So, just as we do this, x equaling 0, and they're a dashed line because you can't see them. It just helps bound our graph, because our graph is never going to touch our asymptotes. And we want to make a table for our values. So if we were to plug in 1/2 into our x, we would come out with 2. We would plug in 1 to our x, we would get 1. If we plug in 2, we end up getting 1/2. Oops. If we plug in 3, we get 1/3. So if we plot these points, go over 1/2 up 2, over 1 up 1, over 2 up 1/2, over 3 up 1/3. And as you can see, our graph is going to look something like this. And it's just going to continue on forever and ever, but it's never going to touch our asymptotes here. Never going to touch either one. Okay? Now I want you to take a second and graph this on your calculator. So take your calculator out and plug in y equals 1 over x. So when you plug y equals 1 over x in your calculator, you should get something like this. If you did not, double check to make sure you have your standard window and you did 1 divided by x here. Okay, so looking at our graph, we have this top part here, that's what we graphed, but we have this second part down here. Okay, these two different pieces, we call those branches. And if you notice, they're symmetrical, so that means if I were to draw a line, something like this, a line like that, and folded it over, they would be exactly on top of each other. And since we have those two branches that are symmetrical, for each point x comma y on one branch, there is a corresponding point negative x, negative y on the other branch. So this first x value that got us the point 1/2 comma 2, and this gave us the point 1, 1. But since we know there is a second branch down here, that is going to give us the point of negative 1/2, negative 2, and negative 1, negative 1. So we're just taking opposite of x and opposite of y. So we can plot all of those points. So I'm going to do that now. So we have negative 1/2, negative 2, negative 1, negative 1. We're going to getting negative 2, negative 1/2, and then negative 3, negative 1/3. So our graph is going to get looking something like this. Okay, so this is the second branch of our graph. And what we call the shape of this graph, we call this a hyperbola. And we should recognize that term. We learned it last semester. So, yeah, a hyperbola just has these two branches. They're symmetrical. And just some more information about this. If our a value is greater than 0, so just the number that is on top here, that would be our a value. If a is greater than 0, the branches of the hyperbola are in the first and third quadrants. Now, if a is less than 0, the branches of the hyperbola are in the second and fourth quadrants. And as the absolute value of a gets bigger, the branches move farther away from the origin. Alright, now we're back to full screen. So, what this is saying is the first and third quadrants, that would be, if we labeled here, this is our first quadrant, this is our second quadrant, this is our third quadrant, and this is our fourth quadrant. A way to remember what order they go in is, since it goes 1, 2, 3, and 4, it makes a coordinate plane, so it makes a C. So start at 1, draw on the C, 1, 2, 3, 4. So that's the order. So if our a value is greater than 1, if it's positive, it's going to be in the first and third quadrant, like this one. If our a value is less than 0, it's going to be in 2 and 4. And as our a value gets bigger, the branches move farther away. So what that would be like, if we had an a value of, I don't know, 5, our branches would just move a little bit farther away. So this distance would be greater. Alrighty, so let's look down a little bit. So now we're going to look at more general. So all of this so far has been on a specific rational equation, but now we're going to focus on all our rational equations. So they're all in the form of y equals a all over x minus h plus k, and they have asymptotes at, excuse me, x equaling h, and y equaling k. Now this is a vertical line, and this is horizontal. Okay, and something just to note about your asymptotes here is, and about really all your asymptotes, it is only true for the end behavior. Now, what I mean by that is normally the asymptote bounds the graph, but it only bounds the graph as x gets really, really big or as x gets really, really small. So your graph may cross these asymptotes at some point. Those are unique circumstances, and we'll look at those in future sections, but I just wanted to make that little side note. So looking at this equation, our vertical asymptote is our x equals h. So looking at this, it's just our value here. So that would be our 6. Our vertical asymptote is x equals 6. Our horizontal asymptote, that's our k value, so the number on the outside. So it's the whole number here, so that is y equals -3. And remember what our domain and range is. That's our x values. And our range is our y values. Okay, so looking at this, what x values can we have? Well, we can have all of them, but do we have any restrictions? So if we have a vertical asymptote, that means we have a restriction. So that means x cannot equal 6. And same with our range, it'll be all real numbers, but we can't have a y value of -3. Okay, so whenever we have a horizontal or vertical asymptote, we're going to have restrictions on our domain and range. So let's try to plot some points here to plot our graph. So before we do that though, we're actually going to graph our horizontal and vertical asymptotes. So we have a vertical asymptote at x equals 6. So that will look like this. Remember, it's always dashed. We have our horizontal asymptote at y equals -3. So it will look like this. Okay, and now to get our graph to see what it looks like, we're going to have to use our calculator. So when we get our calculator out, we need to plug this into our y equals. And what's important is we need to make sure we put parentheses around our denominator. Okay, so because our calculator is smart, it uses the order of operations, and if we don't put this in here, if we don't put parentheses in, then it will take it differently than what we actually mean. Okay, so this is how we should put it in our calculator. We hit graph, and our graph, yeah, will look something like this. It will be in our second and third quadrant here. Okay, because our a value is positive. So to graph, we need to plot 3 points to the left of the vertical asymptote, and then 3 points to the right. So looking at this, we wanted to plot 3 points to the left, so we'd be looking at a point of 5, 4, and 3. To do that, we could hit trace and look at all those points individually, but what's easier is if we just hit second graph, that gives us our table, and it'll show us the values that we want to look at. So I'm actually going to go down, well, technically up, until we get to the values that we want. So looking at this, you should notice that at 6 there's an error, and that's because there is no y value at 6 because we have our vertical asymptote there. So that's just another indicator. So for our 3 points, we could have our 5, -7, our 4, -5, and 3, -4.3. Now we don't have to add in a lot of decimal points because we're not going to be that accurate on our graph anyways. Now I want you to stop this and watch part 2 of the video.